everybody. In this video I'm going to go over homeworks 1.3a and 1.3b. I kind of realized that the lecture material that I'm covering didn't hit all the finer points in this homework, so I wanted to at least walk through it so you guys are more comfortable with how it goes. Okay, so this is the first problem that you are going to encounter. And here we have that here we're talking about the estimation of body weight based on height. And here we have one estimate of the ideal body weight of a woman is shown below. And we want to use this information to answer parts A through B. And what we have is 55 kilograms plus 2.5 kilograms for every inch over 5 feet. And here's the first question. Find a linear model for an estimate of the ideal height of a woman using W for the ideal body weight and for H for height over 5 feet in inches. So the value of H is going to be the height in excess of 5 feet in inches. So if the person was 5 feet 6 inches, H will be equal to 6, and 5 feet 10 inches or whatever, H would be equal to 10. If that's the case, then we are going to have that W is going to be equal to 55 kilograms plus 2.5 times H. The reason I want to point that out is because on a number of occasions we thought that H was going to be equal to the height in inches over 5 feet, which basically meant it was going to be your height minus 60 inches, but that's not the case. It's just simply that. So if you put that in, you should be able to get the correct answer. Let's hope I'm right. 55 plus 2.5 H, and there we are. Okay, and then once again we want to interpret the slope of the model. Okay, now notice here that if H increases by 1, the weight is going to increase by 2.5 kilograms. So if she was 5'1", she would be, if she was 5 feet 1 inch, she would be 57.5 inches, and so forth. So the rate of change of the weight with respect to height is going to be 2.5 kilograms per inch. So what says that? Obviously this doesn't. This says 55 kilograms per inch. This says 55 inches per kilogram, and weight can't change in terms of inches. This is 2.5 inches per kilogram. No, it is 2.5 kilograms per inch. So the answer should be D. Now for part C, we have of the woman is 5.3 or 5 feet 3 inches tall. What does the model predict her weight to be? Well, once again, if she is 5'3", then H will be equal to 3. So we have 55 plus 2.5 times 3. Okay, that's basically 55 plus 7.5, and that should be equal to 62.5 pounds or kilograms, if I did my addition correctly. And I did. Yay me. And then finally we have, okay, if a woman's predicted weight is 72 kilograms, what is her height? Okay, so we have W is equal to 72. All right, and that means we're going to have W is going to be equal to W, which is 72, is going to be equal to 55 plus 2.5 times H, and that means that 2.5 times H is going to be 72 minus 55, or 2.5 H is going to be equal to 17. Okay, dividing both sides by 2.5. We have that H is equal to 6.8. Okay, now we want to round to 1 decimal place as needed. Well, we don't really need to round. We're at 6.8. There's nothing else there. So we can go ahead and put in 6.8. And there we are. We're done. So, one down. How many left do we have? One down, three to go. Okay, so here is our second problem. Here we have the table lists fossil fuel productions as a percentage of total energy for the selected years. And then we have a linear regression model for this data. And notice that y is equal to negative 0.35x plus 95, where x represents the years after 1960. Okay, and the first thing we want to do is once again draw a scatter plot and graph the model on the same axis. And of course we don't need to do that, we just need to select it. Now the first thing we want to notice here is that we have a negative slope. This model right here has a constant slope. This cannot be the graph. So this one is out. The second thing we have is that the y-intercept, the point where the line crosses the y-axis, is going to be at 95%. Well, let's take a look at C. Here, the y-intercept is at, well, notice the divisions here. We have basically 10 divisions between 0 and 100. So it's basically 10% per division. We have 10%, 20%, 30%, 40%. That's like about 48%. So there's no way that can be right. So we know that A and C cannot be the graph. Let's take a look at B and D. Okay, well with B, the intercept is 95, perfect, as we would expect. And D, the intercept is also at, well, hang on, is also at 95%, so that's perfect too. However, notice that this one has a different slope and this one has a different slope. Not only that, the scatter points here are different than the scatter points here. So let's take a look at the scatter points. Notice that for the year 2000, which is 40 years after 1960, we have a production of 81%. Let's take a look at D over here. Now notice here we have 1, 2, 3, 4, 5, 6 divisions that span 60 years. So each division is 10 years. And 2000 is 40 years after 1960. So we have 10, 20, 30, 40. There's our point. Now that point corresponds to 10, 20, 30, 40, about 46%. That cannot be right. So D cannot be right. It must be B. Well, let's just make sure. Okay, once again, here is 40 years, and then 10, 20, 30, 40, 50, 60, 70, 80, a little bit higher. That is indeed 81%. So B is our answer. Okay, the next one is interpret the slope of the model. Okay, here we have the rate. Now notice here, this is our model. It is 0.35 times x plus 0.95. So every single time you go up in year, the production reduces by 0.35%. Okay, at year 1 it is going to be 95 minus 0.35. At year 2 it's going to be 95 minus 0.35 times 2, or 0.7, and so forth. So the rate of change of oil imports with respect to time is 0. Is what's right there. And actually that's the same thing as the slope, which is actually what we're looking for. It's negative 0.35% per year. Check that, and there we are. The next problem is use the model to predict fuel production in 2010. Okay, let me bring this back down. Okay, that's what I'm looking for. Okay, well in the year 2010, that is 60. That will be 50 years after 1960. So for 2010, we will have that x is equal to 50. So putting that into our model, we're going to have that y is equal to negative 0.35 times 50 plus 95. And that will give me 77.5%. So we put that into here. And once again, we are already at the 1 decimal place, so that's not an issue. 77.5, and that's pretty much our approach for that one. And then for the last part of this problem, we want to use the model to estimate which year, the year in which the fossil production will fall below 70% for total energy production. All right, and notice here that we want to round up to the nearest year. Okay, So let's go ahead and do that. We want to figure out when we want to figure this out. We want to basically set y equal to 70%, or 70. That's supposed to be 70. And then we want to solve for x, and that will give us that 70 is equal to negative 0.35 times x plus 95. Of course, we will subtract 95 from both sides. When we add these cancel, we will have that negative 25 is equal to negative 0.35x. Divide both sides by negative 0.35. And we will have that x is equal to 71.42 and some other numbers. Now remember, we want to round up to the next the nearest year, or round up to the nearest year. So that means we want to round up to 72. And then 1960 plus 72 corresponds to the year 2032. So we should be able to put that in. And there you go. Now, all these questions are pretty much variation on the theme. So here we have that the data shows that the percentage of female cigarette smokers in a certain country declined from 22% in 1997 to 14.4% in 2015. And we want to answer parts A through B. And of course, here's the data. Here's the data for both males and female. Okay, so here, let me bring this up a little bit. Here, apply linear regression to the data for females in the table, applying the linear regression produces this model. F is equal to negative 0.42t plus 21.87, where F is the percentage of female smokers written as a percentage, and then time is in years since 1997. So 0 corresponds to 1997. And now we want to draw a scatter plot and graph the regression model on the same axis, and of course we want to choose the correct axis below. Okay, well the first thing is notice that the numbers are consistently going down for the data points. As a consequence, we know this can't be right because here the numbers are going up, so B is out. Also notice that a regression model has a negative slope. Well, that has a positive slope, so A is out. Okay, look at D over here. D has no slope at all. It is constant, so D is out. So the only one that actually has a negative slope and the data basically going down is C. So based on that argument, I'm going to go pick C. And of course, it wouldn't be a good idea to match a few points just to make sure. Okay, now here we want to estimate the first year in which the female smokers is less than 15%. And of course, we want to round up to the nearest year. Okay, so our regression model I have here, it is that F is equal to negative 0.42t plus 21.87, where F is in a percentage. We have here that the percentage needs to be 15%, so we're going to replace F with 15. So we will have 15 is equal to negative 0.42t plus 21.87. We will subtract 21 from 87, both 21.87 from both sides. And that will give me that negative 6.87 is equal to negative 0.42t. Almost messed that up. I'm going to divide both sides by negative 0.42. Okay, these will cancel, and we will have that t is equal to 16.357. Not that that matters. Okay, now remember, we want to round up to the nearest year. Well, if we have 16.35, if we round up, we are going to round up to 17. Okay, and then what are the years, and then what year does this correspond to? Well, since we're talking about the years after 1997, we are going to have 1997 plus 17. That will give me 4, 1, 0, 2. That should give me 2014. And there you go. Okay, so this is the last problem in Homework 1.3a, and here we have a table that consists of the state population and licensed number of licensed drivers in millions for a collection of states, or at least for the states with a population under 1 million. And they created a regression model, and here it is, and it is basically y is equal to 0.74x minus 0.03, where x is the state population in millions and y is the number of licensed drivers in millions for the state. And of course, you'll never guess what the first problem question is. Draw the scatter plot. Let's make this bigger. Draw a scatter plot of the data and graph the model on the exact same axes. Okay, so once again, we're going to use our process of elimination to figure this out. And we're going to start off with D over here. Notice that our model is a constant line. That can't be right because it's supposed to have a slope of 0.74. So D is out. Furthermore, that is a positive slope. This one has a negative slope. So B is out. Also notice that when the population is higher, the number of licensed drivers is higher. For example, at 0.57, we have 0.39. At 0.62, it goes up to 0.43. And when you're as high as 0.96, you have your highest number, which is 0.68. So as population increases, the number of licensed drivers increases. That doesn't happen here. Here, as the population increases, the number of licensed drivers goes down, which kind of makes no sense. So chances are C is out and it should be A. But let's just go ahead and make sure. Okay, so here's A expanded. It has a positive linear slope. And also notice that when, let's take a look at state D here. They have a population of 0.73 and the number of licensed drivers is 0.52. Well, here's 0.7. That's about 0.73 right there, wouldn't you say? All right, and what the number of licensed drivers is 0.52 million, which is right about there, so that data point makes sense. For state A, we have 0.76, that's that point right there, and that corresponds to 0.53, so this one makes sense, so my money is on A. All right, there we are. I did it right, yay me. Okay, the next part is if the population in state H was about 1.4 million, okay, we know that's outside the model, but it says to use the model anyways to estimate the number of licensed drivers in the state. And notice here that they want us to type a whole number and they want this to the nearest thousandth. Okay, let me bring this down and bring up on my OneNote again. Okay, so once again, remember, we have the model is y is equal to 0.74x minus 0.03. X is in millions, and so is y. All right, that state population has 1.4 million, so we are going to have that y is equal to 0.74 times 1.4 for 1 million minus 0.03. And when I do that, I have that y is equal to 1.006 million people. Now notice that they want the total number of licensed drivers. They actually want the whole number, not millions, but as a real number rounded to the nearest thousandth. So this is 1,006,000 people. Well, we don't need to worry about rounding because, well, that's the nearest thousandth right there. So it turns out that this number should be the number that they're looking for. We don't want to put in 1.00. My point in there is we don't want to put in 1.006. We want to put in this, the entire whole number. So that should be 1006000. And there you go. And now it's time for the last part. Here we have the number of the licensed drivers in State J in 2014 is about 1,043,000. Use the model to estimate the population of State J in 2014. All right, so we have that population State J was 1,043,000 people. If that's the case, then for our case, Y is going to be equal to, now this is the number of licensed drivers, not the population, licensed drivers. But if that's the case, then Y is going to be 1.043 million. And now we can figure out what X is. We are going to have that 1.043 is equal to 0.74 X minus 0.03. Of course, we're going to add 0.03 to both sides. Let's remember, we want to isolate X. These will cancel. When we add here, we will have 1.073, and that will be equal to 0.74 times X. We can divide both sides by 0.74 to isolate X, not 5, but 4. And if we do, we will have that X is equal to 1.45 million. Okay, now remember, we want the actual population that rounded to the nearest thousandth, so that will be 1,450,000 people. Okay, and now, of course, we don't need to do any rounding because we're already down to the 50th. We're already down to the 10th of a thousand of persons, so we can just go ahead and put in 1,450,000, and there we are. That is our answer. And that is pretty much the first part of this homework, that is homework 1.3a in a nutshell. Stay tuned for another video that will cover homework 1.3b. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.